All right, Chapter 8, Section 5, Proving Triangle Similarity by SSS and SAS. Both SSS and SAS are theorems that represent kind of the similar concept of what we did in Section 4, if you recall. In Section 4, we had the AA theorem, and in each of these cases, whether the Section 4 AA theorem or in this section, the SSS and SAS, these simply represent ways where I can have minimal information and still prove two triangles are essentially scale models of one another. Without these shortcuts, without these minimal ways to show similarity, I'd have to go through the slightly longer process of showing all three angles of one triangle were congruent to all three angles of another, and each corresponding side was a scale factor k multiplier away from its image and the other triangle for all three sides. Essentially having to show 6 pieces of information to be true before I came to the conclusion that the two triangles, the two shapes were in fact similar. In Section 4, I could get away with simply 2 angles. If I can show any 2 angles of one triangle are congruent to any 2 angles in another, that forces all the above to then be true, that all corresponding pieces are scale factors of one or the other, and angles are congruent. And then here in this section, we're going to explore 2 other ways, namely the SSS theorem today, and then tomorrow's video, we'll talk about the SAS, or the side angle side theorem. So hopefully you realized it by now, either by reading it or by just listening. SSS refers to the side similarity theorem. So I'm going to be dealing with 3 sides of one triangle being scale factors or proportional to 3 sides of another figure. And for the record, a few of you will probably be getting some deja vu from some of the theorems that we had in a Math 1 course on triangle congruence, where you'll see some of these same acronyms, namely SSS and SAS. That's kind of similar to what we saw in a Math 1 course on congruence. The main difference here being that when 2 triangles are congruent, literally every measurable aspect of one is the exact same or copied and pasted into the other. When we're talking about similarity, we are talking about scale models. So that means that they are dilations of one another, to reference what we talked about in Section 1. In other words, one is a miniature of the other, or one's a magnification of the other. But that's going to be the difference between similarity and congruence. Not the same shape, but what we would call a scale model of one to the other. All right, so formally speaking, the side similarity theorem says the following: if all 3 corresponding side lengths of one triangle are proportional to another triangle, then they are going to be similar to each other. And that also then ties in, as soon as I give these 2 triangles the label of similar, that means corresponding angles must also be congruent. So it's a way to kind of bypass that information to tag it all along with that baggage. And over here in the margin, I have written what proportional means. It means to have a common scale factor k. So there's that dilation piece of information right there from Section 1. Okay, scale factor k, some constant multiplier. And the key term there is going to be that's a constant or common scale factor between all 3 sides. I can't have different multipliers from one to the other. That's going to warp the shape. Okay, so for today, let's talk about side, and let's jump right into an example to see how that's going to be applied. All right, for this first example, we are asked the following: is either triangle DEF here in the middle or triangle GHJ over here to the side, are either of these triangles similar to triangle ABC? And again, there's that weighted term similar, which means that are either of these triangles going to be scale models, scale miniatures or scale magnifiers of the original triangle ABC. Okay, and the one thing I want to point out here, one thing that I want you to notice with this diagram is that they give me no information about any of the angles. And because they haven't given me any information about the angles, that's why I'm going to be using this SSS theorem, the side theorem. Also, they do give me actual information about each of the sides, so that's why this one's accessible. So let's jump to the whiteboard so I can go about the solution process. All right, so first off, I am going to be comparing both these triangles to the same triangle, namely triangle ABC. Let me just quickly sketch that. Okay, so here's triangle ABC. And they do tell me a little bit about the side lengths, or all about the side lengths, rather. They tell me that this goes 8, 12, and 16 respective units. Okay, so in these cases, I'm going to be comparing this given triangle, triangle ABC, to two different ones to figure out if either of them are scale models of the other. So the first one I'm going to test here is triangle DEF. And this one is quite apparently a smaller version, DEF, not just because it looks smaller, but also because the information they tell me about the size, that's just fundamentally smaller numbers. So DEF will definitely be a reduction or a minimization if it happens to be similar to triangle ABC. And that's the part we're actually going to discover right now. Because just because this is smaller does not necessarily mean it's similar to ABC. This could have some other weird thing happening that just fundamentally is a different triangle. Okay, so there is a way to test that. And here's where I'm going to again reference something that we talked about in a previous section. It's called a statement of proportionality. Basically, a statement of proportionality says the following. It says that corresponding side lengths, so for instance, AB here is going to correspond to DE here. Corresponding side lengths need to have a ratio, some sort of scale factor multiplier that takes one and turns it into the other. Let me express that with a fraction, right? But that whatever that scale factor ratio is going to be, whatever that reduced fraction is going to be, has to be the exact same as each of the other corresponding pieces. So for instance, BC down to EF or AC down to DF. Okay, so I could create the actual statement of proportionality just to actually write it. I'm not going to actually use this because I'm going to show you a far more easy and shortcut way to go about solving this. But just to write it, my statement of proportionality would be the following. It would say that side AB is going to correspond to DE. And that's going to equal whatever that ratio equals is going to be the same as BC to EF, which is going to be the same ratio as AC to DF. And whatever each of these three ratios reduce to, that's ultimately going to come out to whatever my scale factor K is. Hopefully this statement of proportionality rings a bell from a previous section we talked about earlier last week. Okay, and I could go through this process of actually plugging in these numbers for each of these, but there's actually an easier way to see corresponding pieces here. And it is important to understand how to identify corresponding pieces here because neither of these shapes are actually oriented the same. You can see that this DEF is like kind of an upside down version of what it would be oriented with ABC. But let me just erase this and show you there's actually a simpler way to organize these to figure out which pieces correspond to which. And maybe some of you actually already see it. And it actually has to do with the fact that I actually explicitly know each of these side lengths as they are. They give me all numbers in each of these cases. I don't have any variables, no unknowns here. I know each of the side lengths. So here's a simple way to figure out which pieces are corresponding with which. I have a short side. I have kind of a middle length side, and then I have a long side. And so my short side in this triangle should correspond with whatever's the shortest side in this one. The middle number will associate with the middle number, and the long number will associate with the long number. That is enough to figure out my ratios right here. So for instance, if I were to start with AB, or the smallest of the three lengths here being 8, that's going to correspond with or be in the same ratio with the shortest length here, namely the 6. And that's confirmed. It's AB corresponding to DE. Again, I can get away with this short, mid, and long kind of organization because I do already know all three side lengths in both triangles. If any of these were variables, I wouldn't really be able to use this structure because if I had an unknown, I couldn't actually confirm whether or not it was the shortest, middlest, or longest of the three. Okay, so if there is a variable, there's a different way to go about solving it. And we'll see that in the next example. But for right now, let's finish this up. So next, my middle number here would be 12. That's going to be corresponding to the middle number here being the 9. And lastly, the long numbers 16 and 12. It's just important to make sure that you have the same triangle representation in the same position in the ratio, namely ABC lengths. These longer ones are all in the numerators. And then these DEF lengths, these smaller triangle ones, are in the denominators. And so what I've created are 3 different ratios of 3 different sides. Now, if these two triangles are in fact similar, by the definition of SSS theorem, they need to each have the exact same scale factor k. How do I find that? Simply by reducing each of these fractions. So as I reduce these fractions, it's just a really quick step here. So for instance, with my short sides, 2 goes into both top and bottom, and that reduces to 4/3. Now for the record, this reduction to 4/3, this would be my scale factor, 4/3, the reduced version of this ratio. Over here for my middle lengths, I can see that 3 goes into top and bottom, and that reduces again to 4/3. And that's important that these two are equal to each other. That simply means that the same scale factor is applied with my short sides as with my middle length sides. And just finishing this out, my long ones, 4 goes into top and bottom. It does in fact reduce to 4/3. I get 3 consistent, constant scale factors k. So my scale factor here being all equal, what does this actually mean? What does this imply? That yes, these two triangles are in fact what we would call similar. They are scale factors of one another, scale models of one another. Okay, and again, in order for that conclusion to be met, I would need a constant scale factor. However complicated it may be, as long as it matches between all 3 sides, it is in fact a similarity. Okay, and just to confirm, like, what does that 4/3 actually mean? In some of these problems that you'll see in this section, it will ask you what is k, what is the scale factor if they happen to be similar to each other. It's just reducing that fraction to that 4/3 we did a second ago. 4/3 is bigger than 1. If 3/3 is 1, 4/3 is bigger than 1. That would imply that we're talking about going from triangle DEF here, this direction, and expanding it, enlarging it, magnifying it so that's the same size as ABC. If I wanted to switch directions, I would simply take the reciprocal of that k. In other words, my scale factor that I found here was 4/3. If I wanted to figure out, well, what about a minimization from ABC to DEF, I would simply flip that fraction, and 4/3 would become 3/4. The number would be smaller, and that would represent a minimization. Great. So that's that one. Let's do that one more time for the second triangle, triangle GHJ. Okay, so I'm still dealing with triangle ABC. In this problem, I was asked to check 2 triangles. So here's the second of the 2. And here is that triangle, and here's GHJ. And then I was told the following side lengths. Okay, 10, 8, 16. Okay. So in this case, again, I'm just going to use the same strategy because, again, I was given all 3 side lengths explicitly, so I can just organize them by the longest to longest, shortest to shortest, so on and so forth. So the shortest here is 8. The shortest over here is also 8. So I have an 8/8 ratio for my short sides. This, for the record, does reduce to 1. What does that mean? That means it's a scale factor of 1, which simply means that if this turned out to be a 1-to-1 ratio, one triangle to the other, that would be what we call a congruence. A 1-to-1 ratio means that literally it's the same length, and that's actually shown here, that that's 8 and that's 8. They have the same length. If all 3 sides end up being the same length, then we can quite obviously see that 2 of them are definitely not. But if all 3 ended up being the same length, they would be similar, for the record, because there would be a constant scale factor. That scale factor would just happen to be 1. But more specifically, it's a special type of similarity that we would call congruence. But let's go ahead and finish writing this out. My middle number would be 12 here, and then 10 right there. We'll quite obviously see that this is not reduced to the same value. But lastly, 16 to 16, here we see the 1-to-1 ratio again. And then just confirming my result here, reducing each of these fractions, just like in the last one, 8/8 reduces to 1. 12/10 reduces to 6/5 because 2 goes into top and bottom. 16/16 also reduces to 1. But the important thing to understand here, and I technically could have just stopped with this piece right here, is that since these do not equal each other, that does mean something. It doesn't mean that neither triangle exists or anything like that. It just simply means that they are not what we would call, or let me just write this, not similar. Okay. Again, it doesn't mean that the triangles don't exist or anything like that. It just means that they don't have the designation of similarity. They are not scale factors of one another. Okay. All right. So let's go ahead and erase that. Again, you'll see problems like that where it basically says, all right, test to see if these two are similar. If you are not given any angle information, SSS will likely be the strategy you use. And that is typically given when you have all three sides that you're shown. All right, our last example for today's recording will involve this one right here. In this problem, we are shown these two triangles, triangle ABC and DEF. And we're told to find the value of x or solve for x so that triangle ABC will be similar to triangle DEF. So I am solving for x with a purpose here. I need to solve for the missing piece, solve for the variable that will force these two triangles to be similar to each other. So it's kind of like just another phrasing of what I'm going to be using in order to use the side theorem to show that all three sides have a similar proportionality. So let's jump to whiteboard. All right, so I have triangle ABC. And I have triangle DEF, obviously a larger version of ABC. And then I'm told the following information. And you'll notice a fundamental difference between these diagrams and what we just did. Namely, right here, I am told I have an unknown, a variable. And because of this, first off, I would not be able to organize by short, middle, and long because I just quite frankly don't know how long this one is. I don't know if it's in the middle or if it's the shortest or the longest or whatever, right? And in this case, I'll have another unknown down here for DF. Okay, and my job here in this problem is to figure out what x has to equal that will force these two triangles to be scale versions of the other. But I'm going to use the same strategy here. I need to have a constant of proportionality. Now, here is the convenient part with this problem. These two triangles are oriented exactly the same, but beyond that, they actually tell me the names of these triangles. This is triangle ABC, and this is DEF. And as I've stated before in a previous section, the order of that title, the order of that name, namely ABC, because it's in that order, and it won't always be alphabetical, right? But in this order of ABC, AB are the first two letters, which means they have to correspond with the first two letters of the second triangle, namely DE. So AB, this side right here, has to correspond with DE here. That means that these two are what we would form a ratio with. And whatever that ratio ended up being, that scale factor K after I reduce it, would have to match both of the ratios for the other two corresponding sides. I'll just happen to have an unknown here. And ultimately, I'm going to be using a strategy called cross multiplication to solve for that missing piece. So I could make another statement of proportionality where I compare all three sides to all three sides. So just briefly doing that, I would have the following. I'd have AB to DE equaling BC to EF, these again being corresponding pieces, and then AC to DF. And to finish the statement of proportionality, that each of these fractions, whatever they happen to be, would have to reduce to the same scale factor K, some constant. All right, well, I do know some of these pieces, all right? All right, namely, I know that, actually, I know all these pieces, so I just have to fill it in. So AB is 4, that's going to be related to DE, which is 12, 4 to 12. Right, and I have to use this statement of proportionality. In this case, I can't use short, middle, and long because, again, I have unknowns, so I actually don't know which ones are the longest pieces or not. So I just make my way around the triangle. So BC in this case is not just some number. Here's my unknown of x minus 1, EF is 18, and then AC is 8. That's going to be associated with this 3 times x plus 1. And whatever these will end up reducing to has to be the same value, whatever that ends up being. But in order to actually solve for my variable, I can actually set myself up with an equation that just relates two of these three. So I just have a single equation where I just isolate the variable, thus creating an algebraic equation. So in order to do that, let me scroll down here a bit. So this is absolutely true. Each of these ratios has to equal each other. But let me do this. I'm only going to focus on these guys. I'm only going to set these two equal to each other. I could have set any of these equal to each other, but had I gone with these two set equal to each other, I'd have a variable on both sides. And when I cross multiply it, I'm going to end up with some pretty messy variable stuff. I'd end up with an x squared in that case. I could have set 4 over 12 equal to 8 over 3 times x plus 1, but this is just a slightly simpler version where I don't have to distribute. So let's just go with these two. But if I set these two equal to each other, now I can cross multiply. And again, this is a strategy that you would have learned in middle school, but it's applied anytime I have a fraction equaling to another fraction. I can just cross multiply numerator to denominator, numerator to denominator. So when I do that, I have 4 times 18. I'll throw that on the left. 4 times 18. And that's going to be equal to this 12 in the denominator here multiplied throughout the numerator here, x minus 1. And that's an important distinction. This is a common mistake. When I multiply this 12 times this x minus 1, I'm actually going to be distributing it. So when I do that quick step, 12 times the x minus 1 will give me 12x minus 12. The 12 is multiplied throughout that x minus 1. And then over here on the left, when I do 4 times 18, that's just a real number being 72. At this point, it's a very, very familiar algebraic equation where I'm just going to be using inverse operations to get the variable by itself. Namely, I'm going to add this 12 to both sides, and I'll get 84 is equal to 12x. And then at that point, when I divide both sides by 12, I'm going to find out that x is in fact 7. Now, for the record, I could have, again, done any other combination of setting two of these equal to each other. This just happened to be the simplest of the two. It won't always be the front two. You get to pick and choose, really. I could have done 4 over 12 is equal to 8 over 3 times x plus 1 and gone through the same process. It just would have been a slightly longer process, and that I would have had to distribute that 3 times the x plus 1 first. Or I could have set these two equal to each other, in which case that would be more of the nightmarish one, where when I cross multiplied, I'd end up with like an x squared polynomial. I'd still get to the same result of x equals 7. It's just worth noting that one of those methods, namely setting these two equal to each other, ended up being the shortest path to that result. And technically, I'm done with the problem, right? I solved for the variable. X has to equal 7. But let's see what that actually means. And also look at the different ways that you might be asked questions about this problem. So first off, the actual question here was to solve for the variable. We have done that officially. But another way this could have been phrased is it might have said like, all right, these two triangles are going to be similar. Find the length of BC. In which case, notice that that is not just x, but I have an algebraic phrase here where if I were to plug in x equals 7, I'd actually find out that b to c is 7 minus 1 or 6 units. Over here, it could have asked me what the length of DF was. Again, I could plug in what x is, which is now 7. 7 plus 1 is 8. That 8 times 3 would be 24 units. Okay. So you could have been asked it in that way. Another way to kind of check our work here, right? We've already determined that x is 7. But in order to check our work, we kind of want there to be this constant state of proportionality, this constant k. I want to figure out maybe what the scale factor is. I can actually see that really quickly just looking at these two corresponding pieces, the 4 here and the 12 here, right? I can figure out what multiplier took me from this AB of 4 units to this DE of 12 units. 4 times 3 would get me to this 12, meaning my scale factor is tripling the size of triangle ABC over to DEF. Well, let's just double check that to make sure that still worked out when I plug in x equals 7. Well, if x is 7, 7 minus 1 tells me that BC is 6 units long. And if BC is 6 units long, it needs to have the same scale factor multiplier. So that was 3. So that 6 times 3 would give me 18. That checks out. For AC, if I were to take the scale factor of 3 and multiply it by this length of 8 units, that should give me 24 units down here. And when I plug in 7, 7 plus 1 is 8. That 8 times 3 does in fact give me 24 units. It checks out. So that's how you can solve for the similarity between two triangles when you have an unknown. Again, there's that strategy of cross multiplication rearing its ugly head again. So be aware that that will happen. But that will conclude today's lesson on SSS theorem for side-side-side proportionality. Tomorrow, we'll wrap up section 5 by talking about side-angle-side theorem, or SAS theorem. But that will conclude today's recording.